Now we move to the third part of this chapter, in which we focus on the discharging process of a capacitor and the energy stored in it. After we have studied charging of a capacitor, let us assume that a capacitor is fully charged, having a voltage E and charge Q, as you can see in the figure. Once connected across a resistor, excess electrons on this plate will move and migrate to the other plate. Thus, the positive charge on the capacitor, on this part of the capacitor, will decrease. You can see how the charge decreases in the graph aside. Now, the more electrons leave one plate to the other, the less the charge becomes, because electrons tend to neutralize now. In this case, when we talk about the current, if you remember in the application that we have solved previously, we said I is plus dq by dt, because the current was serving the increase of the charge. However, here, the opposite happens. The current serves the decrease of the charge. That's why it is referred to as minus dq by dt. Now let us study the discharging phenomenon quantitatively with numbers. So first of all, keep in mind at any time t, U of the capacitor equals that of the resistor. The capacitor plays the role of a generator here. At time 0, the voltage of the capacitor is E. It hadn't lost any of its charge. Thus, its voltage is still the same. The current at this instant is I equals E over R, because as we have said, UC equals UR. Now, after particularly 1 RC, the same tau which we described in the charging process is the same in discharging. However, its definition varies. We say that tau is the duration needed by a capacitor to discharge 63%, thus receiving or keeping 37% of its voltage. At time equals to tau, the capacitor will charge another discharge another 63% of the remaining. And if you do the mathematics, 63% times the 37%, we're gonna have the 0.14 times E, or 14% of E remaining. Then eventually after 5 tau, the capacitor is practically discharged completely. We say that the discharging process ends at this time. At an instant, we can always calculate the current by using I equals UR over R. And don't forget, UR is always equal to E. Now, if we take a look at the graphing section, which is shown on the right hand side, at time 0 we have voltage E. At 1 tau, voltage becomes 0.37. At time equals 2 tau, we have 0.14. And at 5 tau, practically the voltage across the terminals of the capacitor becomes 0. So if we join these points, we're gonna have an exponential decreasing graph resembling voltage of the capacitor and voltage across the resistor at the same time. Now, if we want to calculate current, we have mentioned this before. If we want to calculate the current, we just use UR over R, and don't forget that UR equals UC. Okay, so the discharging, the current also discharges and decreases, in fact, exponentially the same way as UR. Now we move to our second section for today, which is the energy stored in a capacitor. Before we start, I would like to point out an important thing related to capacitors. Capacitors store charge. They store positive charge on one plate and negative charge on the other plate. Therefore, the energy stored on the capacitor is electric. And electric energy, as we have seen before, is calculated by QU. Nevertheless, in the case of charging and discharging, the voltage across the terminals of a capacitor isn't constant. It changes with time. Therefore, we require some mathematics, some mathematical tools here, which are the integrals, and calculations are to be omitted right now. So we just focus on the final idea concerning electric energy stored in a capacitor, which is given by the equation W electric equals half QU. Now, we can memorize this equation. Q is expressed in coulombs, while voltage is in volts. Nevertheless, we can always change voltage or charge into other terms. For example, if you use Q or replace it by C times U, the equation becomes half Cu squared. On the other hand, if you replace U by Q over C, as you can see here, the equation becomes half Q squared over C. Hence, an overall equation that you, or set of equations that you can memorize, electric energy is given by half QU, half CU squared, or half Q squared over C. You're not supposed to memorize the three of these equations. One is enough and you can come up with the others. This ends the course for today. Now we'll go to solve an application together so that we focus and we highlight the main ideas that we have seen. So application 3. Let's get started. A defibrillator, which is a device that's used to jump-start the heart. I hope that you haven't seen this in real life. It's okay if you have seen it in movies, in which a certain patient undergoes or has a certain cardiac arrest. His heart or their heart stops at a certain instant. To jump-start the heart, we need to supply it some energy. Well, the paragraph here explains that the defibrillator is charged under a voltage of 1820 volts. Now, when it discharges, it needs 6 milliseconds of time to reach a voltage of 1600 volts. During this time, energy is given to the chest or to the rib cage or to the heart of that person. That energy is enough to jumpstart the heart, and if there is any chance of living, the person will be revived. So, let's go to the mathematics and to the physics of the exercise and solve it after we have talked a bit about the daily life application or the common ideas that we need to know about defibrillators. Calculate the time constant tau, calculate the voltage at the end of 1 tau, calculate the electric energy supplied to the chest and the average power delivered to the chest. So we start by a charged capacitor, then it discharges during 6 milliseconds. Values that are worth mentioning are capacitance and resistance, which are given. Starting with 1, tau equals R times C, which is 50 times 1 millifarad. That equals 50 milliseconds or 0.05 seconds. So the capacitor discharges and its time constant is given by this. To calculate the voltage at time equals to 1 tau, we know that in discharging, after 1 tau, the capacitor keeps 37% of its voltage. So 0.37 times 1820, which is 673 volts. So it keeps this. The drop in voltage is 1820 minus 673, which is not our question now. In the second question, we are supposed to find the electric energy supplied to the chest. So in order to do that, I'll calculate the energy of the capacitor at time 0, then the energy at time t when the voltage across the terms of the capacitor reaches 1600 volts as given. So W0 is half CU0 square, W1 is half CU1 square. U0 is the starting voltage, U1 is the voltage that we have reached, which is given to be 1600. Simple mathematics, and please go over the calculations because there might be a mistake. The answer is 376.2 joules. In reality, if you go and research that a bit, the heart needs around 360 joules to jumpstart. So 376 is a reasonable answer. Okay? Now, going to part 3, which is calculate the electric power delivered to the heart or to the chest. First, electric power, as we know it from grade 8 maybe, is simply energy per unit of time. So I go to the equation P average equals energy over time. Energy supplied is 376.2 joules divided by the time, which is 6 milliseconds or 0.006. The answer is 62,700 watts. So extremely high power is given to the heart. In fact, what jump starts the heart is this huge power, that energy which is delivered during a short period of time. And as I'm talking about this, I remember that in the previous video, we ended the session by talking about the flash of a camera. The same thing holds true over here. To end our session, we're going to talk about a daily life application of capacitors, which we have chosen for today to be lightning and thunder. Upon friction between clouds, they become negatively charged. Electrons pile up on the lower part of the cloud. On the other hand, the surface of Earth will charge positively. Therefore, a parallel plate capacitor is formed between the clouds and Earth, and when the voltage increases to a certain level, because of the charge piled on the clouds and on Earth, electrons will be flushed towards Earth due to that high voltage. Now, the motion of electrons will produce lightning due to friction with air, and they produce also sound, which is thunder, due to the rapid motion of electrons, which will produce expansion, then compression of the air surrounding them. That's all concerning this application. I hope you liked our session. Thank you for your time, and we still have one more session of this chapter. See you during it.